Hey everybody, this is Professor Iris Miano with your Day 20 lecture video for Math 2 Pre-Calculus concerning section 6.6, which is where we get introduced to all of our double angle and half angle formulas, and also going back in time a little bit, a few sections, with section 6.3 concerning trigonometric equations. So I don't have a lot of preamble for either of these two sections. It's mostly, particularly for 6.6, we have a bunch of new formulas to learn, and they are your double angle formulas, which you can see are given by this first box. There's actually 3 different options for cosine of 2 theta, and so there they all are. And then there's one option for the cosine of 2, or sine of 2 theta. Here's tangent 2 theta. Here's another way you could write sine squared theta, cosine squared theta with equations 6 and 7. Here's tangent squared theta as well. And then here in this next little bit are really obscure items. How to do a half angle on a squared trigonometric function for sine, cosine, and tangent. Then we get into our half angle formulas, which have a couple of different flavors depending on for tangent, alpha over 2. And you'll want to be careful about assigning which sign, S-I-G-N, plus or minus to it, depending on the location of the half angle. Okay, so it's a lot to take in, and if we want to talk about the derivation of a lot of these formulas, that's an entirely different discussion. What I want to focus on with you is getting to a point where we can use these formulas correctly. And so that's what I'm going to be focusing on. If you are interested in a a song to help you remember some of these things, I haven't found a lot of good ones yet. I found a pretty dryly humorous video here. I'll let you guys click on that one if you are looking for a good laugh. It's not something that's a tune that I really recognize, but it's something to help you learn your double angle and triple angle formulas. Not that we care about triple angle formulas. It's really just using the sum formulas in conjunction with the double angle. Anyway, if you have some time and want a good laugh, go ahead and click here on the hyperlink. So I think the hyperlink also shows up for the PDF, so you should be able to get it. And if you can't, for whatever reason, I just don't want to waste time in the video sharing it. But if you come across YouTube videos that are presenting helpful songs or just ways to remember these formulas, like how people have come up with memorizing them, or if you have your own songs that help you memorize these formulas, please by all means share them with me, share them with the class. I would just be so delighted. All right, so anyway, I'm just going to go ahead and dive into the practice. So here is my first example, and boy, it is a doozy. So we're going to actually answer 1, 2, 3, 4, 5, 6 questions in regard to the information associated with number 12 here. So the instructions are to use the information given about angle theta, which is to say that its tangent is 1/2, and theta lives in basically the third quadrant, because theta is between pi and 3 pi over 2. And then we'll find the exact value of all 6 of these items here using our double angle, half angle formulas as needed. Okay, so the first thing that we need to do is to recognize that since we're in the third quadrant here, this little piece of information, let me start drawing. This tells us that the sine of theta is negative, and so is the cosine of theta. because that's indicative of the sine and the cosine output values, or inputs and outputs rather, in the unit circle anyway, in the third quadrant. Furthermore, it would be good if we were having a go at figuring out what the sine theta value is and the cosine theta value. So what I'm going to do is use a Pythagorean identity with this information in order to, I'll first solve for cosine. So I'm going to use the following identity. Tangent squared theta plus 1 equals secant squared theta. So tangent theta is 1/2, so go ahead and take 1/2 and square it, plus 1 equals secant squared theta. So then that'll give us this will be a 1/4, and we will add it to 4/4, which is what this is going to be, and so this will become 5/4. So 4/4 is just my way of redefining this 1, so it's a value that I can add to what is now 1/4 by squaring the 1/2. So 5/4 therefore is equal to secant squared theta. And taking the square root of both sides and recognizing that since the secant is 1 over the cosine, right, it's definitely going to be negative. So it'll be negative root 5 over 2, rather. Excuse me. 2 equals 1 over the cosine, which is the secant. So that means that the cosine of theta equals, so if you rationalize the denominator after flipping it over, you will get negative 2 root 5 over 5. I am delighted to give more detail in class if we like, but I'm just going to leave it at that for now. So now we have our cosine theta. Great. That is something that we need in order to come up with, you know, pretty much all of these items up here, A through F. Now let's go ahead and use this to calculate the sine of theta with the other Pythagorean identity of cosine squared theta plus sine squared theta equals 1. Okay, so we know that cosine theta is negative 2 root 5 over 5, so go ahead and square that. And we'll be able to eventually solve for sine squared theta. So squaring all this bit, you'll get 20 over 25. Call this 1 on this side a 25 over 25, and subtract, and you'll get 5 over 25. This value of sine squared theta. Remember, sine theta is supposed to be negative, so when we take the square root of both sides, we're going to keep the negative square root. So therefore, sine theta equals negative root 5 over 5. Okay, cool. So sine theta, cosine theta, we have got them. So we can at least get started with finding the value for part A. So I'll go ahead and change the color now that I'm working on a legit part. So part A, we'll do that in pink. So that'll be sine of 2 theta equals 2 sine theta cosine theta. Now I have the values of sine theta and cosine theta, so that'll be 2 times negative 2 root 5 over 5. That's cosine theta. And then sine theta, oh, so I'm doing this a little bit out of order, but luckily multiplication is commutative, so it's okay. Sorry if that's causing some confusion here. Sorry, that's supposed to be a 5 down here. Let me correct that. Okay, so sorry, technically this is the cosine and this is the sine. I switched them here on accident, but it's okay. I'm closely following my notes, and I happen to do that in my notes. Okay, so we have plenty of slashing to do here. So let me go ahead and do that in green, so it's a nice contrast color. So these negative signs cancel each other out. These two root 5s multiply to give us a 5, so we can cancel out one factor of 5 down below with these two factors of root 5 up above. Hopefully that makes sense to everybody and it feels good. And so what is left? Well, this 2 can technically be considered to be over a 1, and then we'll have a positive 4 over 5 as our final answer there. Okay, now let's do the cosine of 2 theta. And we have a few options for that one, of course. Let's pick a color. What color do I want to do my work in for cosine of 2 theta? Let's do it this orange color, sure. So we can have this be nice and colorful. E is cosine of 2 theta, which will be, out of the options I chose, and this is just a stylistic choice, cosine squared theta minus sine squared theta equals, so square your cosine, which is negative 2 root 5 over 5, minus the square of your sine theta, which is negative root 5 over 5. So that'll give you 20 over 5 for the first one. 20 over 25, that is, sorry. And that should be familiar. It's something that came up back here. We were solving for sine theta, excuse me, and then minus, it looks like 5 over 25. And that'll give us 15 over 25, which reduces down to 3/5. And that's that. That's the cosine of 2 theta. Okay, what's next? We want the sine of theta over 2. So let's change the color yet again. Do this dark green. Theta over 2. Sine of theta over 2. Oh, so the formula for that goes like this. We're going to take plus or minus the square root of 1 minus cosine theta over 2. Now we're going to take the principal square root because we want to notice that theta over 2 is between pi over 2 and 3 pi over 4. So it's going to be positive for the sign, okay? So from there, we can actually plug this stuff in, and, you know, no sign in front just means it's positive. And we'll put in a 1 minus a negative 2 root 5 over 5, because that's the cosine theta. And then that's all over 2. And then here we will go ahead and have this be common denominator for the stuff that's going on in the numerator inside of the radical. So that'll be giving us a 5 plus 2 root 5 over 5, but then that's all over 2. So it's kind of like that, yeah, so it's kind of like the 2 kind of slips in, so to speak, to the denominator there. And we could talk about that more in class if you like. So that'll give us, hold on just a secundo. So that'll give us the square root of 5 plus 2 root 5 all over 10. Okay, so, and we can keep it like that. No further simplification possible for that one. Okay, so that's C. Now part D, let's do cosine of theta over 2. And what color should we use there? let's do this lighter blue. Sure, why not? 2. So that'll be part D. Cosine theta over 2, which will equal the plus or minus, I'm just going to write the raw formula down, 1 plus cosine theta over 2. So that'll be negative, since the between when theta over 2 is it's between pi over 2 and 3 pi over 4, the cosine is negative, so we'll be taking the negative square root of 1 plus a negative root, or 2 root 5 over 5. And then I'll have that all over 2. Doing the same thing here as that first step, making the common denominator and having the 2 kind of absorb into the denominator, it turns out that I'll just kind of go dot, dot, dot. There's some algebraic steps in between, similar to what was done up here, and we will get our final answer of negative square root of 5 minus 2 root 5 all over 10. All right, 4 down, 2 to go. So the second to the last item here is tangent of 2 theta. And what color would we like for that one? Let's go for one of these, the dark purple color. Why not? Cute. Tangent 2 theta, here we come. So E is tangent 2 theta, which is 2 tangent theta over 1 minus tangent squared theta. And so you might be thinking to yourself, oh crap, do I need to calculate tangent theta? No, you don't. That was given to us. The tangent of theta, if you recall, was 1/2. So this is 2 times 1/2 in the numerator, and then 1 minus 1/2 quantity squared. Okay, so then that gives us a 1 in the numerator, 3/4 in the denominator, because 1/2 squared is 1/4, 1 minus 1/4 is 3/4. So basically you take the reciprocal of 3/4 and you get 4/3. Relatively quick and easy on the tangent 2 theta. Okay, and lastly, let's do tangent theta over 2. So let's pick a new color there. Let's go for this, kind of a lighter, what is this one called? Indigo? Okay, we'll do this lighter purpley bit. Okay, so here we go for the last one of this problem. I know, kind of a long one, but it's a nice overview of almost all of the different formulas. So tangent theta over 2 is the plus or minus 1 minus cosine theta over 1 plus cosine theta. And again, you'll need to discover which sign you're going to take based on the location of the angle. So theta over 2, again, still is between pi over 2 and 3 pi over 4, so that means the tangent is going to be negative. So we'll take the negative square root here, and that'll be 5, or sorry, excuse me, I'm getting right to the final answer, but we need to arrive there together, at least with a little bit of work shown. So that'll be 1 minus negative 2 root 5 over 5 over 1 plus negative 2 root 5 over 5. It's all in the same radical. And so that'll give us okay, common denominators happen here, and then we perform the operation, and we'll be able to cancel out the tens. And here's what we'll get in the end. 5 plus 2 root 5 over 5 minus 2 root 5. And yes, there are some algebraic steps in between, and we can talk about them in class if we need to. Whew! So that was number 12, a six-parter. Yikes. But we did get to, in the midst of solving this problem, practice the double angles for both sine and cosine, half angles for sine and cosine, double angle for tangent, and half angle for tangent. I mean, really, we practice it all as far as double and half angles are concerned. So bravo us. Okay, let's move on to the next example, where we're going to use the half angle formulas to find the exact value of the expression here. So take your sine of 195 degrees and say, all right, 195 degrees is half of what? Well, this can be rewritten as the sine of, not sim, excuse me, sine of 390 degrees. Oh gosh, that is so sloppy. Let me try that again. 390 degrees is the double of 195, right? So if we're going to use a half angle formula, which is what they're asking us to do, we'll need to rewrite our sine value that we're trying to calculate thusly, and then plug it into the, the equation. Now 195 degrees, that is like, what is the SIGN of the output there? Well, it'll be negative for the sine. So we'll need to take the negative square root of 1 minus the cosine of 390 degrees. Now 390 degrees is more than 360 degrees, so we're going to make an adjustment there and say to ourselves, well, how much more than 360 degrees is that? Because that'll be the equivalent end location that's going on here. So 390 degrees is 30 degrees more than 360 degrees, so it's actually the same as the cosine of 30 degrees. So we'll take that into account, and then we will take 1 minus what's the cosine of 30 degrees is root 3 over 2. It's all over a 2. So we'll make common denominators happen here, and we'll get negative square root of 2 minus root 3 all over 2. 2 minus root 3 all over 2, but then it's over 2 again, so we get to use that little bit of algebraic trickery to say, all right, that just kind of gets absorbed into that other denominator space in what I like to call the supernumerator, and that'll be negative, oh, whoops, I'm making extra pen marks than I want to, negative square root of 2 minus root 3 over 4. But 4 is a perfect square number, so that can actually come out of the radical, which will have us a final answer of 2 minus root 3 inside of the first radical, and that's all over a 2. And there you have it. So, quite a bit of algebraic manipulation at the end to simplify it, and the main thing that we want to keep in mind is that since we're being asked to use a half angle formula, you want to rewrite the argument of your trigonometric function so that it's something over 2, use the formula, and if you go beyond a full rotation, make adjustments accordingly. Okay? Great, so let's do this one more time, but for a cosecant of 7 pi over 8. So we're now in radians instead of degrees. Nothing we can't handle though. That'll be equal to what? 1 over the sine of 7 pi over 8. That's just converting the cosecant to the way more familiar sine reciprocal function. And then say to myself, okay, well, what do I need to what do I need to represent this as in order to use the half angle formula? Sorry, so that'll be, now bear with me, this is a little bit funky. It'll be the sine of 7 pi over 4 over 2, right? So this will be like your theta as you use it in the formula. So again, it'll still be 1 over, and we'll use the half angle for sine, which is the square root, and it's going to be positive, okay, because 7 pi over 8 is between pi over 2 and pi, and that's going to be positive for sine, okay? So it'll be 1 minus the cosine of 7 pi over 4 all over 2. Okay, so then we have some algebra to do. So 7 pi over 4 is, let's see. What do I want to do as my next step here? What did I do? Oh, so the cosine of 7 pi over 4 is root 2 over 2. So let's go ahead and just throw that in. 1 minus root 2 over 2 all over 2. So, you know, we'll do the usual thing, common denominators, all that is. And we'll get, let's just kind of continue this over here. The 1 over square root of 2 minus root 2 all over 4. But remember, 4 is a perfect square number, so it can come out of the radical. So, oh, also, we want to, how did they do that? Oh, we flip it over. 1 over the radical. So what did I do? Oh, I did a rationalize the denominator thing. So I said that we have a 2 minus root 2 over 4. I didn't bother taking that 4 out just yet. I'm just rationalizing the denominator. Minus root 2 over 4. But this 4 can be a multiplier out in front of this guy right here. So it kind of whoop, right? Parks itself out in front. And then we need to multiply by the conjugate, 2 plus root 2, to get rid of this bit right here, 2 plus root 2, which will then give us, what did I say, 4, okay, so that gives us down below here, 2, that'll be 4 minus 2, which is a 2, and then up top it is 4 times the radical of, so we'll take care of this bit in the same instance, 2 minus root 2 all over 2, so that'll give us a 2 out in front, and then we still have a factor of 2 plus root 2. So then that'll be, oh, and then these 2's will cancel. I know, too much fun. The square root of 2 minus root 2 times 2 plus root 2. And that, believe it or not, is as far as you can go with the simplification. Yikes. That was intense. Yeah, and there's definitely some algebraic nuances that got a little bit breezed over. We can talk about it more in class if you'd like, okay? Cool. Let's go ahead and get into some identities. So much fun. All right, so here I'm going to focus on the left-hand side, which is got more going on, more complex. I'm gonna go ahead and just do this kind of a thing. And I'm going to start by reassigning cotangent and tangent as the cosine theta over sine theta and sine theta over cosine theta that they can be redefined as using that particular rational identity. So here we go. It'll be cosine theta over sine theta minus sine theta over cosine theta, all over, so that's just cotangent theta minus tangent theta redefined. Same redefinitions here, but plus okay. And what do we want to do here? We want to get a common denominator going on. So we need to have the LCD for both supernumerator and superdenominator of sine theta, cosine theta happening. So that means we'll multiply by a cosine over cosine here, sine over sine there, and so on and so forth. And in doing so, we will have the following. So that'll turn into a cosine squared theta minus sine squared theta over sine theta cosine theta all over, again, cosine squared theta, excuse me, plus sine squared theta over sine theta cosine theta. And so much fun, we get to just slash away these sines and cosines, and then just have these two above each other, or on top of one another. So then that'll give us, I'm going to just continue right here and say that that's going to be cosine squared theta minus sine squared theta over a 1, because this is equal to 1, yeah, via the Pythagorean identity, which is cosine squared theta minus sine squared theta, which just so happens to be the way that cosine 2 theta is defined. Well, one of the ways. Identity established. Woohoo! Okay. So let's see, let's do one or two more of these, and then we'll get into trigonometric equations. Hold on just a second. Okay, sorry for the interruption, folks. Let's establish this next identity, and you know what? This one is actually only a few steps long, okay? So here, even though technically this is probably might be arguably a little bit more complicated on the right hand side, we see a half angle for the tangent here, and so I'm going to use a particular half angle formula. I'm going to choose to use this 1 minus cosine v over sine v, because it's going to lend itself. I know there's a couple of options for the half angle of tangent, but this one lends itself better to ending up looking like this over here. Okay, so then I'm going to do what I like to call splitting the numerator after I use this version of the half angle formula for tangent. And I'm going to go, this is equal to 1 over sine v minus cosine v over sine v. Probably see where I'm going with this. 1 over sine v, that's the same as the cosecant v, and then cosine v over sine v, that's cotangent v, which is exactly what I was trying to establish. So I am done with that identity, and we're through with that. Great. Last one, and this one is pretty scary looking. It's got trigonometric functions in it and natural logarithms, but don't worry, as long as we remember the rules associated with logarithms, we're going to do just fine here. Okay, so I'm going to choose to focus on this side of the equation, because this side right here is definitely more complicated than what's going on this side. And by this side, I mean the right-hand side. I'm going to notice that I have natural logs that are being subtracted inside of the parentheses here. So subtractions outside the logs make for division inside the log. So this will be equivalent to 1/2 times the natural log of, keep it in absolute value bars, 1 plus cosine 2 theta all over 2. Okay. Then I'm going to go ahead and what's the word I'm looking for? Oh, I'm going to use this coefficient out in front of my natural logarithm as a mechanism to bring it up as an exponent on the argument of the logarithm, okay? So then that'll become the natural log of the absolute value of the square root of 1 plus cosine 2 theta over 2. Okay, because anything to the 1/2 power, you can reassign it as the square root of it. Okay, and then this 1 plus cosine 2 theta over 2, believe it or not, that whole thing is equivalent to the cosine squared of theta. So, yeah, there's an identity for that. Just get my eyes on it. Yep. Indeed-a-roo. Cosine squared theta is equal to 1 plus cosine 2 theta over 2. So the entire, what's it called, argument, or radicand, rather, is cosine squared theta. What happens when a square root and a squaring get together? Well, they cancel each other out. Watch this. Boom, boom. So fun. And then we are ready to write this as the natural log of the absolute value of the cosine of theta, which is exactly what we were trying to establish. Oh, that other absolute value bar got so sloppy. Let's try that again. Yep, over here. Natural log of the absolute value of the cosine of theta. And we're done. And that was the last exercise that I had in that section. So now we're going to move on to 6.3, in which we're going to be solving trigonometric equations. So, yeah, we're going back in time a little bit. So this is before a lot of the identities that we've been using most recently, before they've been established as far as the way the textbook has been written. So really the only thing we're going to be needing here is the Pythagorean identity. That's the one that's been introduced so far in the story of the textbook. So we'll keep that one in mind. And also, we're going to introduce the idea of inverse trigonometric functions, but we're not going to be using the notation of it, which is just kind of working backwards, so to speak. So we'll be solving some equations, trying to determine which theta satisfies the equation, and there might be more than one theta that does this, and so we'll be referencing back to unit circle a lot. So having your unit circle printout, if you've printed yourself out a unit circle, having that handy is going to be really advantageous for this next section. Okay, so here we go. Let's solve each equation over the interval from 0 to 2 pi, including 0 but not 2 pi, which also is equivalent to 0. Okay, starting with number 14, we want to solve for theta, okay? So the first thing we'll want to do is subtract 1 from both sides. And what will that look like? Well, it'll give us a negative cosine theta is equal to, well, 1/2 minus 1 will be a negative 1/2. So we'll multiply both sides by -1, and we'll get cosine theta equals 1/2. So look to your unit circle, or look in your brain if you have unit circle memorized, and ask yourself, at what theta does the cosine equal 1/2? Well, those will be at theta equals pi over 3 and 5 pi over 3. If you had more than a single rotation going on for your theta, you can list more forever and ever and ever. But listen, we've restricted the domain here on this trig function to just go one full rotation. So that's what will have us just go for these two values as our solution. Okay, great. Moving on to the next one. Let's perform the algebra that allows us to get the trig function alone on one side of the equation, which we'll start off with adding 3 to both sides. That'll give us 5 cosecant theta equaling 5. Divide both sides by 5, and the cosecant, Let's clean that up a little bit. The cosecant theta will therefore equal 1. Okay, but what is the cosecant again? It's 1 over the sine of theta equals 1. So the only way for 1 over sine to equal 1 is if the sine of theta equals 1. Okay, and when does the sine of theta equal 1? Again, reference unit circle. And that'll happen when theta equals pi over 2, and only at pi over 2 within a single rotation. So box it up and call it good. Okay, let's do another one. Number 26. Again, perform the operations to get your, in this case, cosine theta alone on one side of the equation. Let's start by adding 3 to both sides. We'll get 4 cosine squared theta equals 3. Divide both sides by 4. Now cosine squared theta equals 3/4. Now take the square root of both sides. Cool. You want both the principal and the negative square root, and you'll get plus or minus root 3 over 2. Great. When is the cosine of theta plus or minus square root 3 over 2? Well, you might want to break this into 2 cases. Okay, so let's just focus on when cosine theta equals the positive square root 3 over 2. Well, that'll happen when theta equals pi over 6 and 11 pi over 6. How about when cosine theta equals negative root 3 over 2? Well, that'll happen when theta equals 5 pi over 6 and 7 pi over 6. So therefore, all 4 of these values for theta comprise the complete solution set for theta. So theta can equal either pi over 6, and it's conventional to list your solutions in order from smallest to largest. 5 pi over 6, 7 pi over 6, and 11 pi over 6. See what I mean? How sometimes you'll have more than one theta that satisfies the equation. Here's a case in point. Okay, moving on. Ooh, this one's extra tricky because look what's going on inside of the argument of the trig function. How do we deal with this? Well, really you're asking yourself, when is the cosine going to be of what? Now it's theta over 3 minus pi over 4, so there's craziness going on there, but try and ignore that for a moment. If you want, you can do a u substitution and let this entire argument inside the cosine equal to u and just say, when is the cosine of u equal to 1/2? Well, we know it happens at pi over 3 or 5 pi over 3. So now take the entire argument and use it to say, all right, either theta over 3 minus pi over 4, either that whole thing equals pi over 3, or that whole thing, by whole thing I mean the argument of the cosine function, equals 5 pi over 3. And then you have 2 equations to solve. So solving them simultaneously, let's add pi over 4 to both sides. You'll need to get common denominators, and you'll end up getting on this side theta over 3 equals 7 pi over 12. And theta over 3 for this side equals 23 pi over 12. You can trust me or, do the algebra yourself. We'll need to multiply both the sides by 3 here to get, or wait, oh, I did the cross product actually for this one. Or we could, whatever. However you slice it, you're going to be able to determine that this is 7 pi over 4 on this side. And also here, multiply both sides by 3 or do the cross product. You'll get that this other theta equals 13 pi over 4. Okay, now hold on a minute. 13 pi over 4. That seems like it's well beyond 2 pi, right? And we're supposed to be just solving these for a single rotation. So it turns out that we're going to eliminate this as an extraneous. solution because it's outside of the domain, okay? So the only answer that we're actually going to take here is the 7 pi over 4, okay? So be careful for that. If you find you calculate an answer that's outside of the domain, you have to toss it out. Okay, so for the next two examples, we're going to mix it up just a little bit. We're still going to solve the equation, but we're going to give a general formula for all the solutions that are possible, not restricting the domain one bit. We're going to then also list 6 solutions. What I like to do first, though, is list the 6 solutions and then let that guide me into coming up with the general formula, okay? So take a look at this. For what theta does the sine equal root 2 over 2? Well, the first rotation values are going to be, hold on, let me change the color here. Theta is going to be pi over 4 and 3 pi over 4. And then after, like if I go another rotation after pi over 4, what does that look like? 9 pi over 4. And how did I get that? Well, having a denominator of 4 but being equivalent to 2 pi would be what? 8 pi over 4 is equivalent to 2 pi, right? So add that to your pi over 4, your 1 pi over 4, and you'll get 9 pi's over 4. If I want to go full rotation outside of, or around 3 pi over 4, that'd be adding an 8 pi over 4 to the 3 pi over 4 to get 11 pi over 4, right? And then another, 2 pi over that. Around, you'll get 17 pi over 4. And 2 pi, or 19 pi over 4. Would be this. So these are the 6 possible solutions, and it looks like we are grabbing, so this is the formula where you do set notation and you use the set of all theta such that theta equals, let's go pi over 4 and all multiples of 2 pi after that. So this 2k pi is indicating all multiples of 2 pi after pi over 4. And then also you need to do a separate one for this original solution. So theta can also be 3 pi over 4 plus all 2k pi after that, where k is any integer value, positive or negative. Okay, great. Good. So hopefully that all is landing well and makes sense. Let's go ahead and move on to this next example, which is quite a bit more challenging here. So here we're going to have the argument inside the tangent, which is going to be theta over 2. It needs to equal what in order for the tangent to equal -1? So for the tangent to equal -1, that means the sine and the cosine have to be equal in value but have opposing signs. So that's going to happen at 3 pi over 4 and 7 pi over 4. Okay, so theta over 2 being 3 pi over 4, and then also we'll have this separate instance that we'll entertain as well. Okay, so what happens if we solve for theta here? Okay, that'll be doing the cross product. Theta will be 3 pi over 2. Okay, for this first one. And then next, this one will yield a theta of 7 pi over 2. One thing we'll want to remember is that we're dealing with a tangent, which has, originally a tangent function, a parent tangent function has a period of pi. So one rotation is just a distance of pi, but wait, there is an omega modification here, right? So omega in this case, so this is supposed to be an omega. Try that again. So omega, it looks like it's 1/2, right? Technically, being having that theta divided by 2. So the period, therefore, is 2 pi divided by omega. And when you divide by 1/2, it's the same as, oh sorry, pi over 1/2. I'm so sorry, because the parent function here is tangent, so its original period is pi, so if you divide it by 1/2, it's like 2 pi. Okay, so anyway, the period of this tangent is 2 pi, okay? So that means that we need to look for the next revolution, which will be already here with it, because we'll be adding 4 pi over 2 to it, which is the equivalent of 2 pi. So this is already the next revolution. Will be landing on 7 pi over 2. So that is what leads us to have a slightly shorter listing of options that we need in order to come up with the formula. Theta here will be 3 pi over 2 plus 2k pi. Whereas without this modification on the period, you would be iterating by multiples of pi, so it would be by adding k pi. But anyway, we had this adjustment with the period, so that's what made it like this. Oh, sorry. So we've only listed 2 values for theta. We need 4 more. So here the solutions, the 6 solutions are 3 pi over 2, 7 pi over 2, duh. Those are the ones we calculated. And then go, 2 pi, 2k pi more. So 2 pi after this would be what? 11 pi over 2. 15 pi over 2. 19 pi over 2. And 23 pi over 2. Okay, there we go. Great. So those are the only problems that I have of that type. Let's go back to solving equations again over the interval for theta involving just 1 revolution. I'm just going to wrap things up with 2 more examples of this. And here we go. I'm going to choose to redefine this first equation's sine squared theta as 1 minus cosine squared theta. Now, why would I do that? I see that as being advantageous to getting to a point where I can factor it really well. So here we go. Cosine squared theta equals 1 plus cosine theta. Okay, so I can combine some like terms over here, right? These and these can be combined, and also the 1s will cancel out on both sides of the equation. So then I'll have negative 2 cosine squared theta equals cosine theta. And so then I'll add 2 cosine squared theta to both sides so I can have it equal to 0. And it might not be clear why I would want to do that, but I would really like it if I could get everything on one side. Oh, sorry, I meant to do green here. So I can see if I can factor it, and then I can use the zero product principle in order to solve. Okay, so I'm going to do so by taking out a factor of cosine theta here. That'll equal, and then the remaining part in the factored item will be 2 cosine theta plus 1. And here, look, I have done such a fine job of putting myself in a good position to solve now, because I have a product of cosine theta and 2 cosine theta plus 1 equaling 0. So using the zero product principle, either cosine theta has to equal 0 or 2 cosine theta plus 1 equals 0. So here, for what theta does the cosine equal 0? Well, that'll be at theta equaling pi over 2 and 3 pi over 2. Now here I've got a little bit more algebra to do. I'm going to subtract 1 from both sides and then divide it by 2. So I'm really asking myself, for what theta does the cosine equal negative 1/2? And that'll occur at theta's 2 pi over 3 and 4 pi over 3. So collectively, those 4 thetas solve my equation. So therefore, theta equals, oh, and you could use the curly brackets or not. I'll just go ahead and be consistent with what I did earlier. And I want to list these in order of up here. So it'll be pi over 2, 2 pi over 3, 3 pi over 2, and 4 pi over 3. So those are all the thetas. Let's do this one more time and then I will let you go. Okay, so I see an opportunity to rewrite the cosecant squared theta using a Pythagorean identity. So that's what I'm going to do here. Instead of cosecant squared theta, I'm going to write cotangent squared theta plus 1. And that's equal to cotangent theta plus 1. The 1's will indeed cancel. So here we go. And so you'll notice that I'm doing kind of a similar thing with the gathering of terms and the factoring. So that'll be cotangent theta. I'm going to subtract cotangent theta from both sides. And factor, they share a cotangent, oh, hold on, get rid of that. Cotangent theta factor, so that'll be cotangent theta minus 1 equaling 0. Zero product principle dictates either the cotangent theta equals 0 or cotangent theta minus 1 equals 0. So the cosine theta over sine theta equals 0 then, and that means that the cosine theta equals 0. We did that one just a second ago, so that means theta equals pi over 2 or 3 pi over 2. But now we have to entertain this other case in which the cotangent theta equals 1. So that'll be when the cosine theta over sine theta equals 1. So I added 1 to both sides to get from here to here. So that means that we're looking for when the cosine theta equals 1. Oh, excuse me, sorry. Not when the cosine theta equals 1, it's when the cosine theta equals the sine theta. And when does that happen? Well, that happens when theta equals pi over 4 and 5 pi over 4. And there you have it. So just in the interest of quickness and also my laziness, I'll just box up those 2 separate items and call it good. Okay, so again, I want to fully recognize that in the interest of trying to make a timely video of a little bit less than an hour, I skipped some algebraic steps, which I'm happy to go over in class if you like. Thanks for your attention, guys.